sequence of rewrite rules, but you might also make the wrong decision. So if you try to rewrite the multiplication into a cheaper bit shift, you will be stuck and you will not be able to find your desired optimization, which is A. And if you keep applying commutativity rewrite rules, you might also get into an infinite loop. Equality saturation is an optimization technique which addresses this challenge by exploring all possibilities. The advantage is that there is no need to decide which rewrite rule to apply next. And then you can only decide which program variant you want in the end. And the challenge, obviously, with this approach is that you need to efficiently represent and rewrite many programs. And that is why an egraph data structure is used. And the purpose of egraphs is to compactly represent many equivalent programs. So on the left of this slide, you can see an egraph for A times 2 divided by 2. And it looks a lot like a syntax tree, but it's more than that. An egraph consists of e-classes, which are the dotted boxes, and e-nodes, which are the solid boxes. And e-classes can contain multiple equivalent e-nodes. So if you start applying a rewrite rule in the context of equality saturation, you will not go from one program to another. Instead, you will grow the egraph, and so you will grow a set of equivalent programs. Here, for example, the egraphs encodes the fact that you can either use a multiplication or a bit shift according to the rewrite rule below. And you can see that there is one e-class that contains 2 e-nodes. And the e-node is not just the operator multiplication or bit shifts, it's also including its children e-classes. So A times 2 or A shifted by 1. And when you do equality saturation, you will keep applying more and more rewrite rules to discover more possibilities until you find your desired optimization goal. Did I hear somebody?
Sorry. Oh, thanks. Sorry.
Right. So in this case, you can see that A is in the same E-class as the program we started from. So it's we know that they are equivalent, and if we know that A is our optimization goal, we can simply extract it from this graph as our end result. So that is great for arithmetic expressions, but how does it work for functional programs? And to illustrate this, I will use the case study of rewriting RISE programs. RISE is a typed lambda calculus with computational patterns, such as map and reduce. And for the purposes of this talk, I will not talk about the types, but the rewrite rules are typed, and there are types in the egraphs. I'm just not going to show them in this talk. We will focus on 4 rewrite rules that are interesting for RISE. Beta reduction and eta reduction are standard lambda calculus rewrite rules. And map fusion and map fission are optimization rules that are useful in RISE. So map fusion takes a map F, map G, and turns it into a map FG. And map fission does the reverse. And I want to highlight some interesting parts in these rewrite rules. So how can we implement substitution in purple, predicates in orange, and name bindings in cyan in the context of equality saturation and egraphs? So let's start with substitution, which is particularly useful for beta reduction. The simplest way to, there is one thing that is important to realize is that if you look at the substitution of x by e in B, and we are in the context of equality saturation, B and E are not terms. They are E classes from the E graph. So we can't use standard term substitution just like that. And one simple way to implement substitution in this setting is through small step explicit substitution. So we are going to introduce language syntax for substitution, and we're also going to introduce rewrite rules to explain how substitution should behave. And the problem is that this is very inefficient, because every time you will apply a substitution rewrite rule, you will keep adding equalities to your egraph. And so it will grow bigger and bigger, but with a lot of intermediate steps that are not very useful for optimization. Instead, what we would prefer is to have something like a big step substitution over the egraph. The problem is that it's really not obvious to implement. And in particular, you can have cycles in the egraph. So it's really not something you can implement easily. There is another practical approach, which is extraction-based substitution. And the idea is to extract terms from the E classes B and E, which means that you can now perform a standard term substitution, and then you can insert the result back into the egraph. So it's quite efficient, and we know how to do standard term substitution very well, but it's an approximation because we are only considering one possibility from B and E, and we're not dealing with all of the possibilities. In practice, if we look at rewriting a map of 4 functions into 2 maps of 2 functions, we can clearly see the difference in efficiency between the 2 approaches. On my laptop, if you use explicit substitution, you will not be able to find the goal on the right-hand side. My laptop ran out of memory after multiple seconds, while if you use extraction-based substitution, you can find the goal on the right in just milliseconds. So the difference is very important, very huge. Now let's talk about predicates. So in rewrite rules, such as eta reduction, you need predicates to make sure that X is not free in F. And the problem again here is that F is not a term, but it's an E-class, which represents many equivalent terms. So you can think about different ways to deal with these predicates in the equality saturation settings. The first one is to apply the rewrite rule only if all of the terms represented in F satisfy the predicate. And the problem is that you're going to ignore valid terms. So if there is a single term in F that does not satisfy the predicate, you're not going to apply the rewrite rule at all. On the other hand, if you use an exist quantifier and you apply the rule if only one of the terms satisfies the predicate, you're going to start accepting invalid terms, and that is not acceptable. What we would like instead to be more precise would be to filter F into an E-class F2, which would only contain the terms of F that satisfy the predicate. However, the eGraph data structure is not really meant to do that, because if there are some terms that are in common between F and F2, which will be the case, they will end up being in the same equivalence class. So this is not something that can be implemented right now. As a practical solution, we're going to keep the first one of only applying the rule if all of the terms satisfy the condition. Now let's move on to name bindings. So if for rewrite rules such as map fusion, you will have to deal with name bindings, and especially in this case, on the right-hand side, we want to create a new name binding when we apply the rewrite rule. So one thing that you could do is to generate a fresh name for X on every time you apply the rewrite rule. And the problem in the equality saturation setting is that equality modulo alpha renaming is not built into the eGraph. So as you keep applying this rewrite rule over and over, you will generate more and more alpha equivalent programs that will slow down equality saturation, but that are not useful at all for optimization. Instead, what you can do is to use De Bruijn indices, and that brings a significant improvement. The only problem is that it doesn't really give you equality modulo alpha renaming for subterms where you have free variables. And another potential direction that to investigate would be to truly build alpha equivalence into the eGraph, but that has not been done yet. So in practice, if we compare generating fresh names and using De Bruijn indices, the difference is quite significant again. In this case, we want to optimize a two-dimensional convolution, and I'm not going to go into the details of what this optimization is doing, but it requires a sequence of 13 rewrite rules if you don't count alpha and beta reduction rules. If you try to generate fresh names on every rewrite, you will not be able to find this optimization, and my laptop ran out of memory after multiple minutes. While if you use De Bruijn indices, you will find this optimization goal in just 2 seconds. There is something else you can do about name bindings, and that is to try and avoid them completely. And you can do this by introducing, for example, combinators like function composition. So if you rewrite all chains of function applications like f of g of x into applying the composition of f and g to x, you can write map fusion and map fission using a different style. So you will not have to deal with name bindings like in the previous version below, and you will also not need the predicates that x should be not free in f. So in practice, if you use this technique, it enables to discover reordering 4-dimensional loops and tiling two-dimensional loops in 30 seconds. While if you simply use the map fusion and map fission rules that are below, it's not possible to find at all. So again, after multiple minutes of search, you're going to run out of memory. I would like to talk about future work now. So even with all of these practical optimizations that I've presented, we still cannot optimize large real-world RISE programs using equality saturation. And these programs would be matrix multiplication or corner detection, for example. And for me, the main problem with equality saturation, when you want to scale it to really big programs with complex optimizations, is what I've tried to represent on the diagram on the left, on the right, sorry. So if you use equality saturation to go from the little dots that I've called 1 to the dots that I've called 2, it will require equality saturation to search for a certain amount of possibilities, which is represented by the orange circle here. And if you want to use equality saturation to go from 2 to 3, it will require you to explore another set of possibilities, which is represented in purple here. However, if you want to use equality saturation to do the composition of both, so you want to directly find 3 starting from 1, the space of potential programs that you will need to explore is much bigger than the union of the previous 2 searches that you had to do for the individual steps. So that's what the brown circle is representing. And I think that the equality saturation is very good to explore many possibilities, but in practice, we don't actually want to explore all of the possibilities. And that's why I am interested in combining ideas from equality saturation and other approaches to focus the search and avoid searching a really huge space of possibilities when we are talking about real-world programs. And I can see different ways to do this. One of them is deleting or filtering programs from the eGraph, but the eGraph is made to be purely additive. So you can add equivalences in the graph, but removing equivalences is very difficult and an open challenge. I would also like to be able to enforce normal forms in eGraphs. And again, the problem is that if you want to apply a rewrite rule and remove the left-hand side possibility, this is not something you can do with plain equality saturation as it is. I'm also interested in controlling optimizations using rewriting strategies. And in fact, with rewriting strategies, we were able to optimize matrix multiplication and corner detection in previous work. The reason why we're looking at equality saturation is also to bring more automation and search ability to these rewriting strategies. And the final direction that I find interesting would be to leverage heuristics to prioritize promising directions. So equality saturation, in its simplest form, just tries to apply all of the rewrite rules all the time, everywhere. But if you can have a heuristic to tell you when it is more likely to be profitable to apply which rewrite rule. You might be able to avoid searching a lot of unnecessary candidates in the space. Thank you, and I'm open to questions.
Thank you, Thomas.